Hi everyone, welcome. So let M be a three-manifold that's orientable, closed, irreducible, and atoroidal. Maybe you have a mental model for what something like that looks like. There's mine. Here are some motivating questions for my talk. One is it possible to organize all the isotopy classes of incompressible surfaces in our three-manifold? Another vague question is, what does a face of the Thurston norm ball really mean? In the case of a fibered face of the ball, we understand, and I'll talk about this in the talk, how the face corresponds to topological information about the manifold. But what about other faces of the manifold? And the last question is a combination of the previous two. So, is it possible to organize all the isotopy classes of incompressible surfaces that lie over a particular face of the Thurston norm ball, and in some way sort of understand what that face is telling us about incompressible surfaces in the three-manifold? So I'll quickly review the Thurston norm on homology. So if we have some lattice point in h lower 2 of m, and coefficients are going to be real for this talk, define x of alpha to be the minimum of the negative Euler characteristic of all sphereless surfaces representing the homology class. So this is measuring the minimal complexity of the surfaces representing the class, and what Thurston showed is that this function x extends to an actual vector space norm on second homology, so that's saying that it satisfies the triangle inequality, it's linear on race through the origin. And he showed that the unit ball is a finite-sided rational polyhedron. So there's my sort of sorry picture of a finite-sided rational polyhedron. It's supposed to evoke what one of these balls might look like. So let's start talking about surfaces. An embedded surface S in my manifold is taut if it's incompressible and its negative Euler characteristic is equal to the Thurston norm of its homology class. So this is saying that S minimizes the topological complexity in its homology class. There's no topology of S that's not telling you something about the topology of M. The prototypical example is a fiber of fibration of M over S1 over the circle. So there I've tried to draw a picture that evokes that. So I mentioned flows in my title, so now we'll start talking about flows in relation to taut surfaces. So if we have some flow on M, which I'm just going to think of as a nice action of R on M, a cross-section to phi is a surface which is positively transverse to phi. So I'm thinking of the surface being co-oriented, and that means that at every point of S, there's a flow line going through S transversely in the direction agreeing with the co-orientation. And the second assumption is that this surface intersects each flow line. So here's a fact. If I have a surface like this, there's a well-defined first return map, which I'll call F sub S, and that just takes a point on the surface, and the statement is that if I flow forward from that point, I'll eventually return to the surface. And if I take the first return point of the flow to the surface, then this defines a homeomorphism of the surface. And this allows me to think of the manifold as the mapping torus of this first return map. So M is homeomorphic to the product of the cross-section with the unit interval modulo an equivalence relation where I identify the two sides of S cross I using the homeomorphism. So here I've drawn a picture of that. I have my surface, and I take its product with the unit interval, and I have some flow, and I identify the top with the bottom using the map. And because my original manifold I started with is atoroidal, this mapping class has to be pseudo-Nosov. So in particular, cross-sections are examples of these taut surfaces from the previous slide, right? Because If I have a cross-section, this discussion shows that the manifold fibers over the circle with leaf the cross-section. So let's consider this situation. I have a flow on the manifold and it admits a cross-section, and I'm in the first return map is pseudo-Anosov. When is a lattice point in second homology represented by one of these cross-sections? The first thing you might require, if you're trying to give some condition that's necessary, is that for every periodic orbit of the flow, its homology class has to intersect positively the homology class that you're wondering if it's represented by a cross-section. And the theorem of David Fried is that the above condition is also sufficient. So a lattice point is represented by a cross-section if and only if it's positive on the homology classes of every closed orbit. And the second part of the theorem is that if you look at these cross-sections, they determine exactly the lattice points in the interior of the cone over a top-dimensional face of the Thurston norm-ball. So this is saying something about the second question I asked. The face of the Thurston norm-ball, this face F, is sort of capturing the information of this flow on the 3 manifold. So let's unpack that a little bit. If I let C sub phi be the smallest closed cone in first homology containing the homology classes of periodic orbits, I can define a dual cone, which is all the classes in H lower 2 that are non-negative on each closed orbit. And then I have the following picture. So on the left, I've tried to draw what C sub phi might look like. And on the right, I take this dual cone, and it defines exactly the cone over a top-dimensional face of the Thurston norm-ball. So I've tried to draw an example of what the Thurston norm-ball might look like, and I'm going to use the notation B sub x to denote the Thurston norm-ball in the future slides. And every point in the interior of this blue cone, every lattice point in the interior is represented by a cross-section. So I get a bunch of different fibrations of M over the circle, one for every lattice point in the interior of the cone. When I have this behavior, this face F is called a fibered face. I'll also say that the flow phi is canonically associated to F. It's called the suspension flow, and what do I mean by canonically? I mean up to reparameterization and conjugation by homeomorphisms of the 3 manifold that are isotopic to the identity. So this gives a pretty satisfying picture of what exactly a fibered face is telling you about the topology of your 3 manifold. Right? It's saying there exists this nice flow, and the points in the cone over the face correspond exactly to cross-sections of this flow. And if you're trying to extend an understanding of what the combinatorics of the ball tell you about the topology of the manifold, you might ask, what about the classes on the boundary of the face? One first guess about what these correspond to is, well, lattice points in the interior of the cone correspond to cross-sections, which are transverse to the flow and intersect every orbit. Things on the boundary, maybe they're transverse to the flow, but somehow miss certain orbits of the flow. And this guess is not that far off, but let's go further into it. A surface S is almost transverse to phi if there's a second flow, phi sharp, which we get by dynamically blowing up singular orbits of phi, such that S is honestly transverse to phi sharp. What is dynamically blowing up singular orbits of phi? Well, let's say what a singular orbit is first. We're assuming that our flow has some cross-section with a pseudo-Anosov first return map, so a singular orbit is just going to be the forward orbit of one of the prong points of the return map on that cross-section. And a dynamic blowup is an operation that takes one of these singular orbits and pulls apart the singular foliations at that orbit and replaces the singular orbit by a collection of annuli that are invariant under the flow. And so orbits in the annuli will spiral from one component to the other. I'm being a little vague here. more interesting behavior than what I've drawn can happen if you have more prongs. But this is a pretty good picture of what's happening. The idea is that if you do one of these blowups, it allows new surfaces to be transverse to the flow. So here I've drawn the green surface, and you might imagine the green surface is transverse to the flow everywhere except at this singular orbit, it actually contains that orbit. So it's tangent to the flow along that orbit. But after I blow up the flow and replace the singular orbit by this annuli, now the flow actually passes through the surface in the positive direction, transversely everywhere. And it's a general fact that if you have some surface that's almost transverse to phi, so transverse to one of these dynamic blowups, then S is in fact taut. So this allows us to state a theorem of Lie-Mosher, the transverse surface theorem. If we have a fibered face F with this suspension flow phi, and we have some integral homology class alpha, then alpha lies in the cone over F if and only if it's represented by a surface S which is almost transverse to phi. So this is saying, this incorporates the picture of Fried, right? So this is definitely true for the interior of the cone because these are all represented by cross sections, but it's saying that on the boundary of the cone there's at least one representative that is almost transverse to this flow. It's a general fact of Thurston that if you have a fiber of some fibration, then this surface is the unique taut representative of its homology class up to isotopy. But this is not true for non-fibers. So if you have just some random taut surface in your 3-manifold, there could be multiple isotopy classes of taut representatives of the homology class. So what's the point? The point is that this picture of Fried, Mosher, and Thurston uses this flow phi to organize all the taut surfaces over the interior of the face, right? Because cross sections are unique up to isotopy. But it only captures one isotopy of class only one isotopy class of surface per class on the boundary of the cone. So there are potentially some taut surfaces in the 3-manifold that this picture is not capturing. And this is the thrust of the first theorem that I'll talk about today. So if we have a fibered face F of the Thurston norm ball Bx with a suspension flow phi, then for any embedded surface S is taut and lies in the correct cone if and only if S can be isotoped to be almost transverse to phi. So what's the interpretation? It's that this flow is seeing the entire cone up to isotopy, not just homology. Right? We get every isotopy class of taut representative of homology class in the cone, including on the boundary. This theorem is a corollary of a more general thing that I proved about Viering triangulations, which I'll try to state by the end of the talk. And I'll go through the definition of Viering triangulation right now. First, I need to define something called a taut tetrahedron, which is a combinatorial object with the following properties. It's a truncated tetrahedron, and it has some decorations. Each of its faces is co-oriented, and here I'm calling a face, by face I mean a face of the original tetrahedron before I truncated it. So I mean these 4 white hexagons. And 2 of the faces are co-oriented outwards and 2 are co-oriented inwards. And along each edge of the triangulation I have a label of 0 or pi, where it's determined by whether or not the co-orientations match up along that edge or disagree. And I should think of these as specifying an interior angle along that edge. And the tips, I'm going to call the tips the the triangles that come up because I truncated the original tetrahedron. So what's a Todd ideal triangulation? This is a definition of Mark Lackenby. It's basically, what do I get by gluing Todd tetrahedra together so that their decorations are compatible? So face co-orientations should be compatible. That means that I should only glue outward faces to inward faces. And I shouldn't glue the tips to anything. These should get mapped to the boundary. And the angles around edges should sum to 2 pi. So if I have a Todd ideal triangulation of a manifold, here are some observations about it. Its 2-skeleton is a co-oriented branched surface. A branched surface is something like a train track in a surface. A train track in a surface carries curves and laminations in a surface, and a branched surface in a 3-manifold carries surfaces and 2-dimensional laminations in the 3-manifold. And this 2-skeleton, where it intersects the boundary, gives a train track on the boundary, and the complementary regions of this train track are upward and downward flat triangles, which I'm just defining to be these tips of the tetrahedra, where they're distinguished by the property that either 2 of their edges are co-oriented outwards or 2 are co-oriented inwards. And in the first case, I'll call that an upward flat triangle, and in the second case, I'll call that a downward flat triangle. And here's a definition of a veering triangulation. So a Todd ideal triangulation of some manifold n is veering if it induces a pseudo-hyperbolic train track on boundary n. So what do I mean by that? I mean that it splits the boundary of n into a union of annuli that I'll call upward ladders and downward ladders. And these are just annuli that are triangulated by exclusively upward flat triangles or downward flat triangles. And all the upward ladders should be disjoint, and all the downward ladders should be disjoint. They meet along their boundaries. And each ladder should only be 1 edge across. I went through that a little quickly, but what I want you to take away is that a veering triangulation is a special kind of Todd ideal triangulation. And on the boundary, it has this behavior where it splits the boundary into a family of annuli. So there's a picture of what's happening. I'm in my 3-manifold and I'm looking and I see some boundary component. It's a torus. And I have some tetrahedron inside my 3-manifold and it meets the boundary in some flat triangle. And you can see the ladders there. I've drawn 2 of them, an upward one and a downward one. So the tips of the tetrahedra triangulate the boundary and give this nice train track. Here I've drawn what the co-orientations have to be on the boundaries of these ladders. You can see they sort of alternate from one direction to the other as I go around. And for any curve that is not the same slope as the chords of these ladders, if I make it intersect the ladders efficiently, I get a picture like the following. So the curve will go around and intersect ladders, and whenever it crosses from one to the other, the co-orientation is going to be as I've drawn. So these co-orientations, you can think of extending a vector field on the circle, and I'll get some number of sources and sinks. And the number of sources I want to just call the size of that slope. Here's the more general theorem that I proved. Suppose you have some veering triangulation of n, some 3-manifold, and I have another 3-manifold m, which is the Dane filling of n along slopes of size at least 3. Then I want to define the following cone, C sub tau, which is the cone generated by closed curves lying in n, which are positively transverse to the 2-skeleton of tau. Right? So all these curves lie in n, which I'm thinking of as a submanifold of n. And what's true? Then the dual cone which lies in h lower 2 of m, is equal to the cone over some face of the Thurston norm ball. And the codimension of f is the dimension of the largest linear subspace contained in this cone, c sub tau. So this is basically just linear algebra. The more interesting fact is that it's actually equal to a cone over the face. And the last point is was the most difficult. This is that if you have some surface S in my manifold, S is taut and in the correct homology cone if and only if it can actually be isotoped to be carried by the 2 skeleton. And here I'm being a little sneaky by not saying exactly what I mean by carried, right? Because the 2 skeleton of tau is a branched surface in N, and it meets the boundary of N, but it doesn't get completed over the Dane filling that I do to get to M. But I understand how it sits on the boundary of M. So there's a natural definition that you can make about what it means for tau 2 to actually carry a surface when you understand it like that. So let's unpack this. The Viering triangulation is seeing every isotopy class of taut surface over some face of B sub x, and it's not necessarily top dimensional, and it's not necessarily fibered. You might ask, when does this happen? When do the conditions of this theorem apply? Well, if this manifold M admits a pseudo-Anosov flow, phi, with a condition called no perfect fits, then I can define N to be M minus, well, I've written M minus singular orbits. I should really write M minus an open neighborhood of the singular orbits, admits a Viering triangulation satisfying the conditions of the theorem, right? So that means that the Dane filling from N to M has the correct size. So this is a fact it's unpublished, but it's due to Egel and Gariteau. And so when do pseudo-Anosov flows with perfect fits come up? Well, if you have M admitting a taut foliation with one-sided branching, then there exists a pseudo-Anosov flow that's almost transverse to F. This is a fact of Caligari. And this flow has no perfect fits. That's due to Fenley. So the upshot is that whenever your manifold admits a taut foliation with one-sided branching, then we have this flow with no perfect fits, and we can build a Viering triangulation that satisfies the conditions of our theorem, and we get this control of all taut representatives of homology classes lying over a specific cone of the Thurston norm ball. So here's some context. There's a picture of where a Viering triangulation can be viewed as a combinatorialization of a pseudo-Anosov flow, or a combinatorial version of a pseudo-Anosov flow. This is a picture that's being developed by Egel and Gariteau, as well as Saul Schleimer and Henry Sagerman. And there's a parallel picture to the result I mentioned a few slides ago for pseudo-Anosov flows. So there's a condition on pseudo-Anosov flows saying when they specify a face of the Thurston norm ball, but the Viering combinatorics allow us to actually get additional control over the surfaces, over the isotopy classes of surfaces lying over that cone. Here are some words about the proof. What am I actually using to get a handle on the isotopy classes of taut surfaces? Well, if I have my Viering triangulation, turns out there's 2 branched surfaces that are dual to the 2 skeleton that I can naturally define, and these are sort of substitutes for the stable and unstable foliations of a pseudo-Anosov flow, and you can treat them as such. So given my surface, and given some surface that's in the correct homology cone, I want to analyze its intersection with these branched surfaces. Right, so, okay, I've just written that. I have some taut surface in my manifold. I analyze its intersection with these 2 branched surfaces, as well as the 2 skeleton of the Viering triangulation, to sort of systematically simplify that and show that eventually I can actually isotope this thing so that it lies in a neighborhood of the 2 skeleton of the Viering triangulation. So that's my brief summary of the proof. The results in this talk will appear in a paper later this summer, so if you're interested, keep an eye out for that. If you've made it this far, thanks a lot for watching, and I'd also like to thank the organizers of the conference, and in particular James Farr for organizing this special session. Thanks, James.